And again, I was not able to complete, like check your copies. So I'll give a solution in class and then give you the marks and check copies afterwards. Um, if it's still not clear, 1 minute. So is my voice a little bit clear now?
Yeah.
And we will start. We're going to start first solving your worksheet that I provided in the group, and then after that, we'll solve the entire exam question also. Okay. 1 minute. Oh, okay, sorry. I actually haven't created any folder for your A2 classes, right? So, this question, this entire worksheet will only contain questions from your linear momentum and nothing else. That means, again, a similar worksheet like this will be given to you as a holiday homework. Right. In that second worksheet, you're going to get more questions. Like over here, maybe you have like 10 questions, and in the second worksheet, you're going to have 10 MCQs and 10 written questions. Okay, and also provide the marks then, so that in case you want to check your answers with the help of marks, then you'll obviously be able to do that. And after Eid, there will be a very big exam. So now let's not take any exam after Eid. After Eid, we'll start with angular momentum. And after Eid, after angular momentum, we'll start with we'll do a very big exam on entire momentum. Okay, because again, circular motion that we have does not contain this much of content. Like in momentum, we have a lot of contents and queries related, but in circular motion, it doesn't have that much content. It actually takes me on maximum 2 classes to complete the entire circular motion. Now let's start with this. This is linear momentum worksheet 1. And in this first question, it says that there is a tennis ball and that is traveling horizontally with a momentum of zero point 0.4. Just before it is hit with a tennis racket, it rebounds horizontally from the tennis racket and with a momentum of minus zero point 0.6. That means obviously, if this is how a tennis racket is, and the tennis ball was traveling towards the tennis racket with a momentum of zero point 0.4, and this is considered to be a positive direction, and it rebound with a momentum of zero point 0.6, and this was in a negative direction. And all these things, changes and variations, are represented on this momentum against the time graph, and we need to find out the force exerted by the tennis ball on this racket. Now, over here, if you want to find out the force on the force exerted by the tennis ball on the racket, remember that there are two forces exertion over here. The ball is exerting a force on the racket, and the racket is exerting a force on the ball, right? So this is the direction on which the racket will feel the force, and this is the direction on which the ball will feel the force. Now, over here, which one are you trying to find out? Can anyone tell me? The red one or the blue one? No, blue one is the force exerted on the ball, right? We are trying to find out the force exerted on the racket. So on the racket is this one. The ball is exerting this force of whatever Newton is on the racket. I mean, at the end of the day, obviously they have the same magnitude, but it is the direction that is most important to us. Okay. For that ball, the direction will be negative because we are taking direction towards right as positive over here. We could understand that from this first statement given. We're taking the direction towards right as positive and left as negative. I cannot change it because on the question they have given me this direction assumption, right? So I'll not change the assumption used in the question. This is the force exerted by the ball on the racket. And you want to find that. Doesn't matter. I mean, at the end of the day, I've already stated that they are both exerting the same amount of force on each other. So if you can find out the values of force using the change in momentum and time for this entire graph was for ball, by the way, right? So you can find out the force exerted by the racket on the ball from this graph, and that whatever the magnitude is, will be same for the uh, racket also. Only the direction will be different. Now, over here from this graph, this is for, it was already stated, the graph shows the variations of the momentum of the ball, right? So this is for entirely the ball. We can use this information of the graph for the ball's reference to find out the force exerted on the ball, and that will be equal to the force exerted on the racket as well. They both have same forces. Now over here again, the initial the time exactly when the ball and racket comes in contact is 4 seconds, and they move away from each other at 8 seconds. Right? I can read from the graph at 8 seconds. And since you are obviously supposed to taking readings from the graph, you have to draw these broken lines over here in order to indicate that you did took values from the graph. And the time difference over here is what? 8 minus 4, that's 4 seconds. So time difference is 4, and delta momentum, change in momentum, is going to be what? Minus 0.6 minus 0.4. That is minus 0. Is this minus 0.10 or 1? So this is, I think, 1.0 kg meters per second. Now, in this case, why am I getting minus value? Because this was for your ball, right? And that for the ball reference, the force that you're going to get should be negative because this force was exerted onto the ball towards the left direction. That was a negative direction according to my question, and this is a positive direction. So this is the value for change in momentum. Now I can use the derivation that Ft is equals to change in momentum. That means F is basically change in momentum over time, which is minus 1 divided by 4. That is 0.25. So 1 minute, there's actually a time difference problem. The time was not in seconds, the time was in milliseconds. That means you are actually on your graph getting the time as 0.004 seconds, right? Because 4 has to be multiplied with 10 to the power of minus 3, which turns out to be 0.00124 second. So 1 minute, 4 seconds. And now if you guys can calculate it, can you guys let me know the value for this? It should be maybe 250 Newton, right?
Yes,
Answer is over here negative
250.
minus 250, right? You're going to get minus 250. That's because this was the force exerted on the ball, right? So you're going to get negative. But again, as you reference, the diagram again, same amount of force will be exerted on the racket, but in the right direction, in the rightward direction, the positive direction. So that's why the racket's force is positive and the ball's force is negative. So option C is the correct answer. I'll just zoom out, and this is how the entire working is. Is there any problem for question one? Also, the homework that I'm going to give you guys, they will contain obviously MCQs of similar type. I would actually expect all of you to do some workings for all the MCQs which contains maths. I would expect write down all the maths as a rough work for your MCQs and then submit the file. Okay. So for MCQs also do the rough works, show the rough works for the homeworks only. Yes, Saza, do you have any question?
No, miss.
Saza, do you have any question? You raised your hand earlier.
No, it was I was trying to do the thumbs up.
Oh, okay. So, then we'll move on. Okay, this is about question two. A radium nucleus decays by emitting an alpha particle. The student of the recoiling nucleus, wait 1 minute. Okay, this is, I think, about the law of conservation of momentum and Newton's third law of motion. Well, this entire part is not about pollution. This is about explosion. This is about sorry, explosion. Now, over here, it says that a radium nucleus decays by emitting an alpha particle. The speed of the recoiling nucleus is small compared to the speed of the alpha particle. This is because, can anyone tell me what will be the final answer? This is the exact question I used in your notes also. D. D is recoiling nucleus have much larger mass than the alpha particle, right? Um, A is not correct because according to your law of conservation of momentum, everything is conserved, and according to Newton's third law, they will exert equal amount of forces on each other, right? Let me just explain why it is not correct. This is not correct because according to M3, equal forces. Right. Then again, momentum is mainly concentrated in the alpha particle. This is again not correct because momentum, sum of momentum before collision should be equal to sum of momentum after collision, right? Including the momentum for radium nucleus and alpha particle before and after explosion. And the momentum of the recoiling nucleus is smaller than the momentum of the alpha particle. That is again not correct because momentum before collision or before explosion was actually zero. And in order to make the momentum after collision also zero, the momentum of radium should be equal to momentum of alpha particle. Right now, I do not know the symbol for radium, so that's why I wrote capital R. Capital R is for radium. This is your correct answer because according to your mass and voltage ratio, I know the voltage, sorry, velocity, 1 minute, 1 minute. As I was saying, that mass and velocity relationship, we know that they are inversely proportional. Because your nucleus is a very large mass, obviously it will only move with a very smaller velocity, according to this relationship. So let's move to question three. This one says about, I mean, obviously we haven't understood anything about this kind of particle accelerators. We will learn this in chapter 7, but this is not that much tricky, okay? This is not related to particle accelerators, only the using the diagram. Over here, it says that a particle detector shows tracks produced by two particles, X and Y, and they were created by decay of lambda particle at point O. Over here, what exactly happens is that this is exactly on a photographic film, and only charged particles will actually release. Only charged particles will actually, give you some printing on the photographic film. So only charged particles will just release or not really. Only charged particles will just exert some kind of lining. So only charged particle can ionize the photographic film and they will leave some kind of marks that according to this pathway they will follow the entire after the entire explosion. Now over here it says that after the decay by a lambda particle. Like there was a lambda particle at this point. The lambda particle was neutral, so that's why we cannot see this on the photographic film. But after the lambda particle decay, it decayed into two atomic particles. One is X and one is Y. This is exactly the point where explosion is occurring, right? Before explosion, X and Y were combined together under the lambda particle. And after explosion, the X and Y are exploded away from the lambda particle and they are now moving in their reference diagram, right, as they have shown in the pathway. Now, in this part, we are seeing that which of the following statement for the decay should be true about momentum. So please read the four answers and let me know which one will be the correct answer do you think. Over here, mass is conserved. Okay, for example, if this is m multiplied with initial velocity, half m multiplied with velocity, and again half m multiplied with velocity. 1 minute. C and D. Okay, let me see that why the total momentum of this system is zero. The total momentum of this system is, by the system they're referring to the x and y. I do not know if they have zero momentum or not, because zero momentum would indicate that they do not have initial velocity, right? But they do have initial velocity. They do have final velocities. They were moving on this entire pathway. So the total momentum of the system is not zero. That is not the correct answer. And the total momentum of x is equal to the total momentum y. The vector sum of the momentum x and y must equal to that of the lambda particle. Yes, E. Whatever this momentum is, this is before collision, and their momentum will be after collision, right? So the vector momentum of x and y, like vector sum of the momenta of x and y means the total momentum of x plus total momentum of, sorry, plus total momentum of y, they should be equal to the total momentum of lambda, right? This is what your law of conservation of momentum tells you. The total momentum before explosion or collision should be equal to total momentum after explosion and collision. Right, so only option A is correct answer. Otherwise, the others are wrong. The momentum of x is equal to y. There's no point of having them the same momentum. Okay. Now I am entirely assuming that okay, their masses are equal, but from their pathway again, I can see they're not moving with the same velocity. I mean, I know you guys will not be able to understand, but after we have done particle physics from the pathway, we can also understand about the velocities a little bit. See, this velocity and this velocity is not equal. If they're not equal, that means obviously they should not have equal momentum. And to be honest, doesn't matter if they have equal momentum or not. That will not be a case over here because their sum should be equal to momentum of the lambda, right? If they are equal, that will not make any change. That doesn't mean anything about the conservation of momentum. Okay, so this is not correct. Total momentum of the system is obviously not correct, and because they have velocities, they were moving in this entire pathway, they were not stationary. And even though lambda was not represented on this graph, that was solely because lambda was not charged. That's why it could not analyze the photographic film surface, but lambda was there and lambda was moving. Okay, so they have velocities over here. And the vector sum of the momenta of x and y must equal zero. Now they should not be equal zero because the total momentum of these lambda particle was not zero as it has some initial velocity. It was moving with some velocity, so total momentum before explosion was not zero. So total momentum after explosion should also not be equal to zero. Is there any problem for question 3? Then we'll move on to the next one. Here it says the following are four possible graphs for a quantity y plotted against quantity x. So this is y-axis, this is x-axis that they have stated in the first line, nothing to read. Then in second line, which graph best describes or represents y, where it is kinetic energy of an electron and x as its momentum. Now, these are the changes of for a momentum in motion. And on the y-axis, you have kinetic energy, and on the x-axis, you have momentum. Okay, so try to find out that which will be the possible correct graph for the relationship between kinetic energy and momentum. Because on the y-axis, you have kinetic energy, and on the x-axis, you have momentum. So obviously, this is about a relationship for kinetic energy and momentum, right? On the y-axis, you have. Why do you think that? I'll just give you guys some time to think and then reply. Reply with a correct answer. Or is not correct, you guys, if you think that whatever the answer is correct, you guys can refer to that. V as kinetic energy is directly proportional to momentum square, right? That is your answer. Because we know from our basic derivation, right? If you even you start with the kinetic energy and momentum, there's only one equation that connects them, which is kinetic energy momentum square over twice mass. I can actually write this as kinetic energy 1 over 2m multiplied with momentum square. And this entire thing is actually a constant because mass of an electron is constant, right? 1 point, not 1 point. This is 9.11 into 10 to the power of minus 31. That is the mass of an electron. So that is again a constant thing. This entire 1 over 2m is constant. I can resemble this into the equation for y is equals to ax squared. Right? This is exactly the equation for a quadratic equation. And for quadratic equation, this is how the quadratic graph looks like. It has a. That means maybe it was transformed a little bit or translated a little bit, right? From our, I think, P1, right? In levels P1, you know, this represents the transformation. And in this case, A can never be negative, right? 1 by half m is always positive because mass is positive, and 1 by 2 is a scalar number that could not ever be negative, right? So 1 by 2m is always positive. So if that is positive, then this is how your original graph maybe was in this kind of shape, and it will be a little bit shifted, right? So this is how the graph looks like. On your graph paper, they have only provided this section of the graph. And that's why option B is the correct answer. And obviously, I think Abir also said that kinetic energy is directly proportional to the momentum square, and that's right. And I just I'm just explaining this in terms of graphs basics. That since it's y is equals to x squared, so obviously the graph should be a positive quadratic graph, happy shape graph. Is there any problem?
No problems.
Then this is it. Question 4, we'll move on. Now these are for your practical questions. Now, this question 5 says how tiny bacteria move is of interest in nanotechnology, and mycobacteria move by ejecting slime from nozzles in their bodies. Okay. This is how maybe the scenario would be. This is a mycobacterium, and exactly the mycobacterium is going to excrete some kind of slimy liquid in order to move forward. Okay, it doesn't have legs and other arms. So obviously it needs to provide some force in order to move forward. In this case, this is exactly the situation for explosion, and I can write this in terms of either law of conservation of momentum or either Newton's third law, right? If I want to explain this in terms of law of conservation of momentum, then it would be that before explosion, the mycobacterium and slime were connected to each other and they do not have any velocity. So total momentum before explosion was zero. And after explosion or after ejecting the slime, the mycobacterium and the slime will move away from each other. I am assuming the slime has a smaller mass and the mycobacterium has a larger mass. According to your equation, momentum is equal to mass velocity. Objects with larger mass can only achieve smaller velocity. So after ejecting, what is this? The bacteria will move away from the slime or move in the opposite direction to that of slime with a smaller velocity compared to slime because it has a larger mass. Right? Is my explanation clear to all of you?
Yes.
So
Yes.
I'll just write down the answer in detail. This is a very repetitive pattern question. I think I have already told you guys that in Unit 4, you guys will see a lot of repeating questions. So I would suggest maybe memorize that model answer for this. Not exactly memorize, but understand how am I writing the different points and explaining the situation. And you can, copy paste this entire situation for every different answer. Just maybe have to change the term. For example, in our exam or our in our notes, right? I use the equation for or situation for radium nucleus and alpha particle. Over here, you just have to replace the terms with radium nucleus with bacteria and the alpha particle with the slime, right? That is the only difference. Otherwise, the final answer will always be same for every situation. Now, over here, we'll just write that I should not write explosion because they are using ejecting, right? They're not using itself the explosion word. So I'll just use the words represented in the question or used in the question. So before ejecting, you can also write this in your exam paper. The sum of momentum before collision is zero. So yeah, must move. So not conserve. Please read through this entire answer and let me know if there is any problem. Yes, Saza, please ask.
I have two questions. So for
Mhm.
this question specifically, if you're going to explain it by by the Newton's law, would you say something like, because of Newton's third law, there are opposite forces, equally
Hmm.
opposite? And then
Right?
would you
That will
mention
be
Newton's second law about resultant forces?
obviously always. Whenever I'm going to mention Newton's third law, I'll always connect that with Newton's second law.
And then I was looking through question one again, and I just wanted to ask again where you got negative 0.1.
Actually, none. Oh, sorry. I think we're talking about this one, right? Because I got negative 0.1, so it's like negative 1. That is because this was entirely on using the information about the ball, right? And this change in velocity is for the ball and on 0.25 also, negative 25 later also. This negative 25 is indicating that This force was exerted in the left direction on the ball, right? And we are trying to calculate the force exerted on the racket. We want to find out for the racket. So for the racket, the force was exerted towards the right direction. And for this maths, we stated that the right direction was positive and the left was negative. So that's why whatever the value of the force you got for the ball in the negative direction, exactly that will exactly that magnitude you will get for the racket also in the positive direction. This was for the ball's reference. We calculated everything using the ball's information. At the end, I just use that for the racket's force also because they have equal forces.
Okay.
Now, if I go down, is there any problem with this part? For anyone else? Okay, then no problem. We'll move on. State the principle of conservation of momentum. What is this? This is a two-mark question, by the way. So, what is the answer for this question?
Momentum before collision is equal to momentum after collision provided in a closed system.
In a closed system, will not work.
Oh, no external force.
No external force acts on the system, right?
Yes.
I think in a closed system is a nice name for chemistry. Okay, sorry, for some reason I got disconnected from my tab. So finished. As I was saying, the part B of this question 6. Now over here, this one says that the diagram shows two gliders are on air track and the magnets on top of the gliders are repel each other. That means we are facing the north poles together. You can see in the diagram, north pole facing north pole. And the mass of the glider A is 300 gram and the mass of the glider B is 100 gram. That means glider A is heavier than glider B. Since glider A is heavier, obviously if these two magnets are going to repel each other, magnet B will repel or move away using a higher velocity than magnet B, magnet A, right? And magnet A has a larger mass, it will only repel back with a smaller velocity. This is also an example for explosion, by the way. Now this one says that glider A is given a push to started moving towards glider B, which is initially at rest. Oh no, this is not about explosion, sorry. This is about collision theory, scenario one, right? Because scenario two, because glider B was at rest and glider B was pushed towards glider B, and only glider A initially has a velocity. Glider B does not have any initial velocity. And describe how you determine the velocity of A during before the gliders interact and the velocities of glider A and B after the interaction. That is, how will you calculate the velocity of glider A and both glider A and B after this collision? And you may add anything to the diagram to show the additional apparatus required. So if you're using air tracks, right, what are the things we're supposed to use over here to measure that velocity? Can anyone tell me? How do we actually use air tracks? For air tracks, we assume that object is moving with constant velocity. Yes, obviously we have to use light gates, and for air tracks also there's one big assumption. Let me just write this down. First one assumption is that if I'm going to find out the velocities for one particular point, okay, only consider that for that specific particular point on air track, object is moving with constant velocity. Okay, so at any particular point, object moves with constant velocities, and this is the case. Okay. Now after this, if we move on, assumption at any particular point, object moves with constant velocity. Okay. Now we have to use light gates at different sections. I will use a light gate over here. And then again, there's another light gate with this pair, right? This is your first light gate one. Let me just draw a very separate diagram over here to indicate that exactly how we use the main function of light gates. Okay. Obviously, these light gates are connected to some kind of devices with monitor so that we can see the screen, right, where the time is being recorded. This is like a monitor where we can understand that the time is being recorded. Now, what exactly happens in a light gate? A light gate will simply release light and the other one will receive light. Okay, this is a transducer type of thing. It will release light, and this is a receiver type of thing that will release light. So I'll just label this. This is your transducer or releaser. I just write transducer. Okay? And this is your receiver. Okay. Now for this case over here, obviously the receiver will continue to receive a light until there is a block in between them. And what will be the block? The block will be your gliders, the length of your glider. For example, this is how a glider look like. Okay. and the length of this glider will be considered as L. So when this glider will actually pass throughout this, in between these light gates, it will create a blockage. So 1 minute, I'll just take this and I'll just draw a different light glider. The wideness, the height, that doesn't matter. Only the length is a matter for your time calculation. Okay. So when this, I'll just rotate this. So when this glider will actually enter at this point. It will obviously enter in this particular method. That when your glider will actually enter at this point, which is the starting point, where some portion of your light received by the receiver is being blocked, right? This is where the timer will start counting your time. That from this point, the entire light receiver is not receiving any light. And this is the point where the blockage has entered. And after this, all this time, the time is still calculating that the timer is still measuring the time because time is still blocked or this light is still blocked over here. Like all this time, light is blocked. The receiver is not receiving any light, and it will continue until at this position where some portion of the receiver is now starting to get light back, and then the timer will start stop the time. So at this position, when it is about to enter the light gate or some portion of the light gate is being blocked because of the glider in between them, the timer starts on, and when at this position, when the glider exactly is about to leave the light gate and some portion of the light is being received by the receiver, and then your timer stops, right? So for this time you're actually measuring the time for what? You are measuring the time for this distance, right? For the length of your card. Okay, you're not measuring the time for the length of the distance traveled on the light gate. You are measuring the time taken for this length of the car to travel in between the light gates. And for this situation, obviously your object was moving with constant velocity. For this specific point, your object is moving with constant velocity. And if your object was moving with constant velocity, what was the equation for constant velocity? Can anyone tell me?
Distance over time.
Displacement over time or length of card over time, right? So this is your situation. The timer starts on 1 minute. And this is the situation where the timer it stops measuring the time. This is timer on, and this is timer off. Okay, and this during this distance, obviously your object is moving with constant velocity. That was the assumption over here. At any particular point, object moves with constant velocity. That means now, if you want to use the length of your car using a like you can measure the length of your car using a meter ruler, and the time has been measured for you using the time gates, right? So now you can write velocity is length of card, or not card. Over here we're using gliders. So length of glider divided by time. Right, this is how you're going to use the air track and gliders to measure the types of velocity. And also light gates to measure the different types of velocity, initial velocity of glider A and also final velocities of glider A and B. Is there any problems with this part? Now
No,
again,
no problems.
again, I will have to place another light gate. Okay, light gate two. Sharon, are you in class?
Yes, teacher.
No, I didn't have anything from your side today. So, okay. Now, this is your light gate two. We do not need to actually place another third light gate to measure the final velocity of light gate A because after it has moved very close to light gate B, it will ripple back in this factory, right? So I can use light gate 1 entirely to find out the initial velocity of light gate A, and again I can use light gate 1 to find out the final velocity of your what is this? Glider A, right? So there's no need of placing another different light gate to measure the final velocity of glider B because glider B will move within the same backward direction. So I hope that's clear. This is your light gate 2, and this is what we're supposed to add to the diagram. This is light gate 2. Now we have to write this answer. This is a star mark question, by the way, as they had contained every 6 marks, and I actually forgot to copy that star mark. Okay, this is from maybe 2016 or 15, I don't remember. But I have already stated that all our worksheets will be taken, the question papers will be taken from 2014 to 2020, 18, or 2019 on maths. Okay, this is from 2016 maybe. Now over here, it should be clear that they're giving you 6 marks. The first one is that we have to use a light gauge to measure the initial velocity of particle A or glider A, right? And then a second light gauge has to be placed on the opposite side to measure the final velocity of glider B. That is the first case. Whatever you're going to add in this and whatever you're going to measure using those added instruments. And then again, we have to measure the length of the cards or length of the gliders over here using a meter ruler. And this is what we're going to measure over here. And, the gliders should be, sorry, the light gates should be connected to a computer, right? And the entire light gates should be connected to a computer. So now, so far we got one, two, three, four marks. And then another mark they will give you for that velocity is equals to length of gliders divided by time, right? Time taken from the data logger. That is for 5 marks. 1 minute. Yeah, I think they're giving us the 1 mark for the arrangement of the points. There are no other points over here to measure actually. So these are all the things. Or maybe, they could consider that measure the length of the card using a meter ruler. You're also mentioning another device, right? Another instrument. So that could also provide you with the one different mark scheme point. But that depends really on the mark schemes, right? But yeah, I mean, I think over here that was the only source over here for a different separate point. Other than that, no, nothing I missed over here for the explanation. So we'll start with the working that wait one minute. This is 4 questions to type. Okay, let's start with this that even place one light gauge at this age. This is what at the left corner of air trap, and it will measure the initial velocity and final velocity of particle A or glider A. Of particle B, we will place one light gauge at the left corner of air trap to measure the time for initial velocity and final velocity of particle A. Sorry, made a mistake. And final velocity of particle A. And another light gauge at right corner to measure the final velocity because particle A does not have any initial velocity, right? So that's lighter. Another light gauge at right corner to measure the final velocity of glider B. And then again, I can measure the length of the two gliders using a meter ruler. Oh, sorry, wait 1 minute. We're also supposed to write the light case should be connected to a computer to measure the time, or should be connected to computer. Okay? Computers, and again after this, we're going to write that we will measure the length of gliders using meter ruler. Actually, over here the gliders never pass through that light thing. It is the magnet on top of the glider that will pass through the light waves. Okay, so we should measure the length of the magnet, not the gliders. So we should measure the length of the magnets or whatever they have on top of the gliders. We'll try to measure the length of that object. In this equation, we're using magnets, so we will use magnets for the reference of our answer. Length of magnets using meter ruler. There's no need to know like complexity using micrometer, screw gauge, or vernier caliper. Obviously, those will give you a much more accurate length, but there's no need to use of that. Use those things. You can just use a meter ruler to find out the length of this magnets. And finally, using the equation, V is equals to length of magnets divided by time taken to measure the velocities. We have three velocity to calculate, so it will be better to write velocities. Right. So this is your final answer. I'll just zoom out so you guys can see everything and let me know if there is any other problem. Okay, we'll wait for others to read the answer and let me know if you have any problem. Hmm. This class is like that I am teaching maybe students who can't speak because no one turns on their mic. Everyone uses emojis.
Sorry.
Thank you for replying with your voice. Okay. Now, again, this is actually for Unit 6, to be honest. I mean, yeah, this is the Unit 6. Unit 6, Unit 3, air waves, then gliders. These are all concepts for Unit 6, but as I've already stated, that all the descriptive parts for your Unit 6 will actually come in Unit 4 and Unit 5. Okay. And Unit 6 actually will not ask you questions about the descriptions, what is happening, why is that happening. They will not ask you about that. Unit 6, we will ask you questions from calculate the uncertainty over here, calculate the velocity for this light beam, calculate the momentum. All the calculations will be in your Unit 6. And all the description parts, where all the 8 core practicals in 18 will be in this part. Okay. Also, another thing, in A2, Unit 6, it will also ask you basics about Unit 3 also. So you cannot forget the core practicals and everything you did in Unit 3 is. You have to memorize or remember those and take that like, and add them with the concepts about Unit 6 and then sit for Unit 6 exam. Okay, so Unit 6 is basically a combination of Unit 3 and Unit 6. Whatever you studied in Unit 3, that will also be asked in Unit 6. Now over here, this is the before and after velocities. And now we want to find out that if it does uh, follow the conservation of law of conservation of momentum or not. Now they have given this in centimeters per second, but then again their masses were also given in grams, right? So no need to convert anything, or you can convert them if you want to, but otherwise gram in centimeters per second is acceptable value for momentum also. Now in this case, total momentum before collision and total momentum after collision. For total momentum before collision, the particle glider A only had some velocity, which was 5.2. So we're obviously assuming. Also, I'm considering direction towards right as positive. Before collision, this is how they were moving. A was moving towards B, and A had a velocity of 5.2. And after collision, they were obviously moving away from each other, right? A was moving in this direction, B was moving in this direction. So if I'm considering direction towards right is positive, so this is positive, and this one will be negative. So in that sense, 300 multiplied with 5.2 minus 100 multiplied with 2.7 plus 1, sorry, this is 300, 100, 7.5. So how much do you get on the left hand side? The 300 multiplied with 5.1. What is the value for it?
1,560.
1560. Okay. And on the left hand side, I think it should be 1560 again, right? So yeah, it does follow the conservation of momentum. That is a final answer. Okay, now we are done with this question 6. Let's move on to the next question. There we can see that two students are watching an action film in which, I forgot to ask, is there any problem in this part?
No. Not
Yes, I don't know if I did the
I'm sorry, what?
I don't know if I did the calculation wrong, but for the other side I got negative 60.
Negative 60. Can you please recalculate it? 175. That's 2.5. I'm not sure if you can understand my handwriting. That's 2.7 and 300. This is 100 and 7.5.
Yeah, I'm getting negative 62.
You're also getting negative 60. 1 minute. Wait. Just let me do the calculation of it. No, I am also getting negative 60. Then the momentum is not conserved. 1 minute. Let me just see if I'm not wrong. Velocity of A after interaction, velocity of C after interaction. That is 2.7 and that's 7.5. And B has a mass of 100. A is 300. Mhm. Yeah, there is no miscalculation. That means obviously the momentum was not conserved over here, right? Since after collision, with the velocities they have provided, it indicates that the momentum after collision was not conserved. It gives you minus 60, so obviously momentum is not conserved in that case. I thought it would be a conserved situation, but no, you're getting a negative 60 over here. So which means momentum is not conserved at this time. We recalculate it. Plus 100. You're getting minus 60, then yes, momentum is not conserved. I mean, they were also asking that if this results confirm the momentum is conserved in the interaction, so you would write that no, momentum is not conserved. That is the final answer. I hope that's clear now, right?
Yes.
Thank you. Now then we'll move on to the next question. This is about two students that are watching an action film in which a car drives down a road onto the back what? Oh, onto the back of a moving lorry, and both are moving at high speed. The car slightly faster. The car was slightly faster than the lorry. Obviously, the car has to be slightly faster than the lorry because it needs to overcome the distance, right, for which lorry was ahead in order to actually jump onto this part. Now, again, one student complained that this is impossible because the car would not be able to stop before hitting the cab of the lorry. And this is the cab of the lorry. And they are also saying that the car has a max 1250 and is moving at 28, and the lorry has a max speed 3500 and it was moving at a velocity of 25, and the length of the flat back of the lorry allows a braking distance of maximum of 5 meters. Okay. And using all these informations, they are asking that by considering both momentum and energy, show that the start is possible, provided the minimum force of about uh, 600 newtons slows the car down. And you should support your explanations with calculations. Treat the situation as one in which two objects are joined together. Like they're also saying that obviously this is the situation where scenario 3, right? Before collision, they were moving in the same direction separately, and after collision, they combine together and start moving in the same direction with a combined velocity. Now let's do the calculation over here that if that 5 meter distance is enough for that car to come to rest from 28 meters per second to zero over a 600 Newton force applied onto the car. Right? These were the informations given in the question. Now, in this case, let's just identify what would be the final velocity after the two particles will combine together and start moving in the same direction, right? So, I'll first use the law of conservation of momentum. That is total momentum before collision is equals to total momentum after collision. The total momentum before collision, you have 1250 multiplied with 28. They were both moving in the same direction, and even before and after the collision, they're always moving in the same direction. So, in this type of situations, you don't need to assign any direction as positive or negative because this is not for double motion momentum, this is for just single motion momentum. 1 minute. Plus 3500 multiplied with 25.5, and after collision is 1250. This 3500 will actually move with a combined velocity, and this time divided by the 1250 and 3500. Can anyone please calculate the value for your final velocity over here?
26.2.
26.2 meters per second. Okay. Now, after this again, they have given you what? They also ask that you can use concepts about energy also, right? So let's just identify if the total kinetic energy and total total kinetic energy before and after collision were equal or not. So kinetic energy before Ke is what half, mass was 1250 multiplied with 28 whole square. This is for car. And then again, we have to calculate that for the lorry. Please calculate the car's kinetic velocity. 490,000. 490,000. And for the lorry, 1137,975.5. Okay. 1137,975. Okay, I'll just write 1138,000. Okay. Now add them together to give me the final total kinetic energy before collision. 1628,000. And then again calculate for this kinetic energy after collision. 1630295. 1630295. Now in this part 1630295 joules, I can understand the kinetic energy is not conserved, right? Before and after collision, some energy was lost. So let's find out that exactly how much energy that was lost in this equation. Energy loss. Energy loss is the subtraction of the two values 1628,000 minus 1630295. How much is that? This again? 1630 295.
Peter, shouldn't it be the other way around?
Oh yeah, sorry. No. How many? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Yeah, it should be the other way around. Sorry. One after kinetic energy, after collision, they have a higher kinetic energy. Sorry. 1630. Right. That was 30. That was 28.
You get 2295 joules.
2200.
95.
Okay. For Nabila, she's getting a different value. 1 minute. Let me just calculate. That's 220, yeah, that's 2,295. Nabila, can you please check your calculation? Answer should be exactly 2295. Please redo your calculation and let me know if you're getting the same value. Now over here for the energy loss, I have to also show that, right? That the maximum provided force was actually in this situation was about 600, right? This is not exactly 600, this was about 600. So that we can actually understand, we can actually find out that also. Because what energy loss is basically work done over here, right? So work done is force multiplied with distance, and the maximum distance it can travel is this 5 newton. Okay, I think I will look at the same answer. And force multiplied with 5. And over here, if we just make that force the subject of this formula, 2295 divided by 5, how much do you get?
459.
459. This is not equal to 600, right? Or about 600. Let me see if we did any miscalculations over here. I think for that velocity, right, since this was not exactly in a whole number, for that this answer, sorry, the final velocity, as the final velocity of this combined particle was not in whole number, for the final velocity, this entire kinetic energy after collision also had some modification. Let me just do that. 1 minute. 550 multiplied with 28 plus 3500 multiplied with 5.5 divided by 50 plus 3.00. You're supposed to get 497 by 19. Okay, I'll just use that 497 by 19. Now, if I change the answers over here to 497 over 19, then I'm getting 0.53500 plus 50 multiplied with, this is 497 divided by 19 whole square. Okay, and that should give you 1625,059.211. Okay, I think that's why your answer was wrong. I mean, there's no possibility that after the collision, the energy would increase, right? But for your after collision, we were getting greater value of energy. That was not possible. So this is 25,059 joules, and then I'll have to redo the calculation again. 1 minute. 1628000 if multiplied with 5, and then 5 becomes 1628000. Then you're supposed to get 2941. If you divide that with 5, you're supposed to get approximately 588. And 588 is what? According to one significant figure, yes, 588 is close to 600, right? So that means this is possible because the force that should be like applied on the car to make it stop before it can hit the front, it can hit the back of that cab from the lorry is 600 high, 600 newtons or about 600 newtons. So approximately 588 is able to make this entire car to reach rest, sorry, I will say to come to rest before it could hit the back of the car. Is this clear?
Yes.
Teacher, I feel like I don't understand this situation. Like, I understand the calculations, but how it applies to the question, I don't understand.
Okay. Let me just read the question again. Over here, the situation was that the first student considered that this is entirely impossible, that the car will fly off a certain distance and land on the back on the space over here of the lorry and will not hit this back part of the cab. right? That was impossible, but the student learned. And student two said that no, this is possible and we can calculate that also. And we need to prove that the student two is correct. Also, there was a case that if for this 5 Newton, or they've already stated that the maximum braking distance of the car on this lorry is a 5 meter. So we need to show this that exactly how this 5 meter distance will actually be utilized by the car to exactly come to rest and will not hit this cap portion of the lorry. Okay, is a question clear to you, Abhi?
Yeah.
But then again, over here, for the calculations, first thing, they have provided you with the initial velocities and they have not provided you with the final velocity. Okay. In the final section, obviously the car will be on top of the lorry, so they are connected to each other and they will move with a constant velocity. Okay. But I'm assuming that the car will obviously turn off its engine when it lands on the lorry, right? And because the car is moving, because the lorry is moving, then because of the motion of the lorry, all of a sudden the car will also have to move forward a little bit, right? That is because of the same concept that happens to you inside the car. When you are sitting stationary, inside a stationary car, you're both at rest. But all of a sudden, if the car is moving, you'd also have to move forward, right? Because of same reason, if the car lands onto the lorry and the engine is off, but the lorry is still moving, in that case, the car will also move in any direction at the same speed. Up to this, is there any question?
No questions.
Now we need to find out the final velocity. We have the initial velocity and masses available. So obviously we have to use your law of conservation of momentum to calculate this. We calculate the final velocity. And another thing, over here they've also provided that in order to make this done possible, there should be a minimum force of 600 that slows down the car. Like the minimum force of 600 is the resistive force in order to slow down the car before it can hit the front part of the cab, right? Before it can hit the front part of the lorry, right? So we have to prove that actually, according to our calculations, are we getting that 600 Newton force or not? So in order to connect force now, they've also gave you hint about energy, right? So obviously we have to use the energies in order to connect it with force. That's why we used before kinetic energy and after kinetic energy, and we can understand the energy is not conserved, right? Some energy was lost, and exactly why the energy was lost because some energy was used to do work in order to move the car, in order to make the car stop down, in order to make the car slow down, and that energy will be used over a 5 meter distance. If we just divide this energy, change in energy over 5, we'll get the force applied onto the car for this work done. Is this clear?
Yeah, I understand this.
This was the entire working for the answer, by the way. But there's nothing else to explain. This is your entire solution. This is the answer. So you guys have to write this answer in the given space. Is there any question from any one of you for this question 17?
No questions, teacher.
No, teacher.
No.
Practically speaking, I think Tarushi is having some internet problem. We will not actually solve question 8 and 9. 8 and 9, this will be added with the holiday homeworks. Okay, so this is holiday homework 1. Like I'll not provide a different file. This is your holiday homework 1 and this is your holiday homework 2. And in addition to that, there will obviously be a different worksheet which you have to also complete. Okay, so these are going to be with your holiday homework and also another worksheet. A worksheet 2 for the linear momentum. And then again, for the exam paper that you guys did, I can make a video on that and then send you the solution within this holiday. Okay. Whenever I'm free, I'll make a video on it and send it to you because we cannot solve this within class time today. So give you the working or solutions for those exam paper within next week. Okay, so the solution for the exam paper will be given to you guys by next week. Is there any problem from any one of you?
Teacher.
Yes.
So next Sunday, because of Eid, we won't have a class, but Tuesday we will, right?
So on Tuesday, we won't have our class. We're going to start our classes from next week, Thursday. In that case, our classes will start from the 21st.
Okay, so that goes for statistics as well, right?
No, for statistics, we can have, yeah, no, that will be for statistics as well, right? But then again, I'll upload the statistics classes, class durations and homework in your classrooms for maths. Okay,
Okay, teacher. Thank you.
okay then, thank you for joining the class.
Okay, so we're going to solve the rest of this linear momentum worksheet. So this is question 8. In the last, to the last part, we completed up to question 7. Like these were the sections we solved so far, and let's move on to the last two questions for this worksheet. Now, over here, question 8 says that uranium 238 nucleus decays to a thorium 234 nucleus. And according to the nuclear equation, this is the equation we need to identify the particle. I can easily identify that. It says that on the total part, you have the total mass as 238, and it was broken down to create 234 thorium. That means obviously four mass numbers were ejected in form of the particle. So you have 4, and then again 92 minus 90 gives you 2. So this is 2 that leaves you with alpha particle. So alpha particle, right? That is your final answer. Then moving on to the next part B. The particle is emitted with a speed of this much velocity and with a kinetic energy of this much. We need to use this data to show that the momentum of the particle at the instant is about this much. Since like about this much means that your answer should approximately be close to 9 into 10 to the power of negative 20. And again, as I'm using the data for velocities and energy, kinetic energy, to calculate the momentum, I obviously do not have the mass for the particle over here, right? So in this case, I'll start with this situation that kinetic energy is equals to, sorry, kinetic energy is equals to half mv square, and I can just make mass the subject of this formula. It will be twice kinetic energy divided by v square. So that is the expression for mass. And now I can use this derivation for mass and the velocity given in the question to find out the momentum. So for momentum, equation was mass times velocity. Mass can be broken down in its own derivation now, which is twice kinetic energy v square multiplied with v. I can understand these v and v would be cancelling each other out, and you will be eventually left out with twice kinetic energy over velocity. Now I have everything. I just have to input those values into this following equation for kinetic energy and velocity to calculate the final momentum of this particle. So it is going to be twice. Kinetic energy is going to be 6.58 multiplied with 10 to the power of negative 13 divided by 1.41 into 10 to the power of 7. And you're going to get a value of 9.33. Like as I've already stated that the value should be approximately 9, not exactly 9, right? So this is the final value for momentum that you're going to get. Okay, let's move on to part C. When a decaying uranium-238 nucleus is at rest means the momentum before collision was 0 kilojoule, like kg meters per second, and the thorium nucleus moves away with a speed of this much in the opposite direction to that of the particle. The particle, every time they refer this about the alpha particle, right? Now again, they want to find out that explain with the aid of calculation how this is consistent with the principle of conservation of momentum. I already know that this is how the entire thing is working. Previously, at the very start, you only have uranium 235, so 238, and then it decays into two particles, and the two particles will move away from each other. This is the thorium or what? Yeah, thorium 234, and this was your alpha. Okay. Now I already know that in order to conserve the momentum, if the momentum before explosion, this is before explosion. If this is 0, that means the total momentum after explosion should also be 0. So how can that be 0? As they're moving in opposite direction, like as alpha and this thorium 234 are moving in opposite direction, then they must have the same magnitude. So eventually they will cancel each other out, and at the end, the total momentum after collision would eventually be 0, restoring the conservation of the principle of conservation of momentum. So let's start. I already know that momentum for the alpha particle was 9.33. 9.33 into 10 to the power of negative 20. Now, if this one turns out to be negative 9.33 into 10 to the power of negative 20, then obviously it restores with the concept and theory that total momentum after explosion would also be zero, right? Now we just have to prove that, and we can prove that using the mass and the velocity of the thorium 234 particle or nucleus. So momentum for thorium 234, it's going to be 2.4 into 10 to the power of 5 multiplied with 389 into 10 to the power of negative 25. So yes, you are getting the same value, 9.33. This is approximately 6, so I'll just consider writing it as 9.34 into 10 to the power of negative 20 kg meters per second, right? And now you have to include a statement that since alpha and thorium, they both consist of the same magnitude of momentum but in opposite directions, so they will obviously cancel each other out, restoring the total momentum before collision, before explosion. So they will cancel each other out. Restoring the principle of conservation of momentum. The total momentum before collision is equals to total momentum after collision. Okay, so we're done with this question 8, and let's move on to the next question. Question 9 says the photograph shows an arrangement of a Newton's, arrangement known as Newton's cradle. 5 steel balls are freely suspended from a frame. One or more balls on one side will be pulled back and then released so that they can collide with the remaining balls. Okay. Now, this is how this entire thing is working. We are taking 2 balls and then moving it backwards so that they can collide with other remaining 3 balls. And eventually, after colliding, other 2 balls from the opposite side will move away and then again come back, and this entire process will continue in a repetition process. And they're saying that the student makes these 2 measurements. Mass of each ball is this much, and the student, so speed of the 2 incoming balls at impact is this much. Okay. By the way, this is the combined velocity and these are the separate masses, right? So in that case, calculate the total momentum of the 2 balls, 2 moving balls before the collision. Okay, I can clearly calculate that. 2 moving balls, right? 2 moving balls means that they have the combined velocities, but their masses are different. So it's just going to be that this theory, mass plus mass, sorry, mass plus mass moving with the combined velocity, right? So for momentum over here is going to be mass plus mass over combined velocity. That's 0.024 plus 0.024 and eventually multiplied with that 0.88. So now if you calculate that, you're going to get 0.4224 kg meters per second. But then again, all the questions in your, like all the data in your question used to correct to 2 significant figures. So we will also keep our answer to 2 significant figures, but it was supposed to be 0.0. So 0.042 kg meters per second. Okay, that was it for part A. Then for part B, show that the kinetic energy for the 2 moving balls before the collision is this much. Similar concept, I know that the equation is what? For kinetic energy, it's half mass v square, right? As they both have a combined velocity of 0.88 and their masses will be added together. So it's just going to be 0.024 plus 0.024 multiplied with 0.88 whole square. And eventually you will get an approximate value of 0.18, so 0.0185. So I'll just write 0.0186 joules. Okay, that is your approximate value. And then like obviously if you keep these two significant figures, this turns out to be exactly 0.0919 joules, right? That was your answer. So then we'll move on to the next part, and they have a spreadsheet. Part C says that the student notices that the number of balls moving away from the collision is always the same as the number of balls released, which means that if you're going to move away two balls, then obviously on the other side, after the collision, only two balls will be projected away. So to understand why two balls move away after this particular collision, the student uses a spreadsheet to model the situation. He applies the principle of conservation of momentum to find the theoretical speeds of each different number of balls would move away together, and he also find out the kinetic energy of these balls would have. So this is your spreadsheet. First one says the number of balls moving away after collision, and B is mass of balls moving after collision, and the speed and their kinetic energy. And for part one, it says state the condition required for total momentum of all the balls to be conserved. Obviously, no forces, no external forces should act on the particles, right? Provided that no external force acts on the system. That is your second. That is your one condition. The other condition was that kinetic energy should be conserved. Like all these equations of conservations of momentum can only be used for collisions that are elastic collisions, not for inelastic collisions. So let's just write down the answer as they're only looking for one answer. So just write that provided that no external force acts onto the particles. Okay, now this is part one. For part two, it says show that the value in cell C8 has been correctly calculated. Okay, cell C8 is this one, and you need to show that if this has been correctly calculated or not, as this is the velocity, and we have the mass that is 0.072, and we also know the momentum, right? I mean, for all cases, momentum is conserved. So I already calculated momentum in part A1, which was 0.042. I know the mass, I can easily calculate the velocity. So velocity is going to be 0.042 divided by 0.072. And now if you calculate this, you're supposed to get 0.5833, sorry, 58, no, 5867. This obviously corrected two significant figures, turns out to be 0.59. So obviously that is correct. And then again, what would be a suitable formula for the calculations of D9? Now D9 was this one, and this is for kinetic energy, right? Kinetic energy is what? Half into mass into velocity square. So this was your mass and this was your velocity. And for D9, we would have to use, what is this? B9, right? Block B, column 9. So B9 and C9 twice, because C9 is for velocity. And for kinetic energy, we use velocity square. So using the cell numbers, the formula would actually be kinetic energy is basically half mass velocity square. So kinetic energy is in the cell D9, half is a number, mass was in B9, and velocity was in C9, so C9 square. So this is how it will be, or you can also write this as half B9 multiplied with C9 multiplied with C9. That is the formula that will be required to calculate the D9 or kinetic energy of that four balls together, right? Yeah, this is it. We are done with the linear momentum worksheet one, and that is it. We want to solve more momentum worksheets. Now, this was only one linear momentum worksheet containing very tough calculations, then graph readings, MCQs, and also what was this? Air tracks, right? Light gates. And if you want to solve more questions on momentum, also for angular momentum, then please find out the link below to buy our worksheets and also the solutions for the worksheets. You can buy only the worksheets and mark scheme. You can also buy the worksheets, mark scheme, and solve PDF. And you can also buy our worksheets with video solutions. So the prices will be different for different combinations. If you are interested, you can follow the link below, or you can also WhatsApp us in our WhatsApp number. Or you can also email me, that is muhimamed01@gmail.com. Thank you for watching.